Hi everybody. Today we will be talking about the project under title Enhancing UAV Operation Integrating Real-Time YOLO for Improved Situational Awareness. The work have been done by James Ong, David Kim. They're both master students at Cal Poly Pomona. I'm Dr. El-Hadedy Ali, and that's with collaboration with Dr. Shang from the US Navy. So the motivation of the work focuses on adding the smartness in the drones in a way that we'll be able later on to use natural language processing like GPT pods for controlling the drones. Either they're going to be text based or going to be based on the audio based, which later on will be translated to the text based. The project is really huge. It's basically we are using natural language processing. We started with the baby steps using BERT as a first step. As you can see, BERT standing in the middle here. But in the final end, that the drones, it will be equipped in a way that there will be a feedback control. The feedback control using a bunch of really advanced lidars and cameras and all of this extra to be aware how the drones is going around, and based on the coloration of what we are actually taking as a command, plus the feedback, the drones will figure out the directions and the mission it will do. So what is the flight software that it is running on our future drones? So there is a bunch of the flight software exists. One of them is CFS, which is basically there is an open source for it. It's a runtime operating system. And then, there is another version which is ITAR based, which is used for the International Space Station. It's a bus technology and a software based runtime operating system. But the other one, which is really quite famous and have been created by Jet Proportional Lab, which is called F Prime, which is focused on operating on the real-time system, but is really containerized in a small version, basically optimized for small flying and space elements like cube satellites, and it's based on peer-to-peer component communication. So as you can see in front of you, there is an XML component specification is looking into the component-based class and the component tester-based class, and all of them together, it will be going into the implementation of the component. When I say component, this component gonna be like a driver talking to the telemetry, talking to the camera, talking to maybe you can have security, you can have a computer visions, you can have natural language processing, whatever that you would like to add. But if you dive into the component, you will find three different part of the component. There's a passive component, there's an active component, and there's a queue. And later on, you will be surprised by this queue part that we are using. But anyway, the passive is an active component, have their dedicated thread to perform function upon request. While the active, it's a passive component, use the thread on active component when called upon. So, it's a flip back. And then, the queue, it's literally like a queue is a FIFO, first in, first out. And later on, when we'll be talking about, the scheduling the data in the level of the application, RabbitMQ will be doing the same job as a queue. Then what type of ports in a software-based flight software we are dealing with? There is an output port, there is synchronized port, there is asynchronized port. So to make it very clear to the ground, so the output port is an active component need at least asynchronous port to differentiate themselves from the passive component, but it can handle 3 connections. So up to 3 connections you can run into the output ports. While in the synchronized ports, there is a clock coming here, and you don't need to be actually working with a supporting asynchronous port. While in asynchronous port, this is dealt with, they're going to be dealing with the queuing part that we mentioned in the previous slides. So that's a software part. But drones or flying elements need a real board that's computing perspective that's going to be running such a kind of things. And what type of board exists in the market can do that? Microcontrollers. I mean, it's something well known, have been tested for generation after generation, but it's actually not capable to do fancier stuff that we are looking for when we say awareness. So one of them is actually to combine F prime on a SoC system on chip is like PingZ. There is 2 different type of actually FPGA supported SoC, since it has an ARM Cortex, which is basically based on a RISC architecture. There, if you look into the hardware-based people that really like hardware, it's a 6-layer based PCB. It's an ARM processors with a field programmable gate array to support the controllers or the component that it will be mapped later on for the F prime. So we start doing the benchmarking of the ping for the F prime. We found out that, we are studying the memory operations. We are looking into different type of module that and component have been created by JPL, which changed a lot of them, which is basically exponential modular. And we also created a security module that is working with as a lightweight cryptography, which is called gauge hash function for hashing the telemetry information to assure that, the data when it's handled between drone to the other within a swarm, it will be secure enough. And we also use a kind of like a power detector to measure the runtime of how much consumption of the energy from the battery that is operating this type of boards. You will find out here in the memory operation, we have been running multiple comparison between the Z2 versus Z1, which is both of them FPGA SoC based. And, we find how from here we are looking into the computation time. We are looking also the transmission of the data from point to point inside the F prime and the execution for the commands. And those three important parts for dealing with the F prime in terms of memory consumption. Then we are moving into the second component we played with, which is the modular exponentials. As you can see in front of you, the graphical part on the left side, you will find that we were taking 400 messages. We taken the average, the size of this message is a 50 kilobytes, and we are reaching the peak of just running ARM without even dealing with overlay architecture by involving the fabric of FPGA associated with the ARM processors. Then, looking into the energy and the memory, and also looking for the measure time of the unit for the modular measure of the modular exponentiations, you will find something really quite interesting here in front of you about the energy consumption between Z1 and Z2 as a two possible board from the FPGA world. Then, we are here talking in the slides more about, one of the cryptography algorithms, the lightweight base, because we are talking about F prime is supporting small flying elements. And this is based on something in a mass called sponge construction based. It's hashing the data without taking too much energy, and running this in the F prime on the ping Z1 and Z2, showing you that how much energy and CPU utilization will be used for both Z1 and Z2. And the next slide is going to be showing you more details about how much energy consumption for both. Now we are going into a very interesting thing, is YOLO as a computer vision, because end of the day the drone will be looking in the surroundings. So if I give example of go in the top of the building, this is not just like a command. This is basically I'm saying go turn on the right component that it will help you to figure out the surroundings. In that case, YOLO as a computer vision and OpenCV in that case will be looking into the surroundings, giving feedback to the model, and then the model will say go into the place. So let's say that I figure out by the lidars and YOLO I'm going into the building, and this is the specific building I want, but here is the altitude and how distance from the ground, and from there I will go up. To do that, you need an embedded architecture. What embedded architecture in the systems exist in the market we can use? Bitscope is a bunch of Raspberry Pi connected to each other. It's really quite heavy lifted, and it's most likely was used and intentionally for building and simulating supercomputers instead of spending billions of dollars on doing that. This Pi 6 Super 6C, this is really quite interesting prototype. Instead of having a switch, uncontrolled networking switch connected to a bunch of Raspberry Pi, they put everything in the PCB and they put the chip onto it, but it's powering up by 16 gig of SSD for each node, and each node is compute module 4. The second is a Turing Pi. It's a kind of a same try of the Disk Pi 6 Super C, but it can help you to add GPUs like Jetson Nano and Orion. But Jetson Nano by itself, it was a really great thing for people and developers to use for the operating systems and also looking for the computer vision, until the massive number of upgrading of the software. NVIDIA didn't run in to do that. So end of the day, it's a kind of like obsolete, and it cannot be helping that much. And from the practical perspective, both James and David, they did a great work of making this happening, but they were handling a ton of errors coming from missing libraries that does not exist anymore and not supported. Looking into the architecture, you will find out that Bitscope, it's a 48 Raspberry Pi node. Turing Pi, it can be combination of Raspberry Pi and NVIDIA Jetson. Disk Pi is a bunch of Raspberry Pi Compute Module 4. Cluster Hat is not exist in this presentation, but it's really quite interesting. You can have a bunch of Raspberry Pi ZW, which is really quite cool to use for some extent of F prime. Suitability is basically, as I said, large scale. Turing Pi is AI, which is really quite cool for the computer vision as well. And Disk Pi is small to medium scale cluster computing. And you will see some really interesting results coming soon between the Disk Pi versus the Turing Pi by the end of the talk. Processing of the power, because end of the day, I'm not going to be every day taking the Cube satellite back to the Earth, it's changing the battery and sending back, right? So I care about the battery will be staying there for the rest of my life, up to 50 to 60 years. Then, primary applications, as I mentioned, is a bunch of applications, but we are hitting the ground to find even more application in the space application for such a kind of architectures. I keep saying YOLO, but what is this YOLO? It's a computer vision based. It's a trained, already pre-trained model. They already have up to 8 YOLO versions. For this specific presentation, we are actually working into the 5. 5 is more suited and more stable to be running in the Turing Pi and this Disk Pi Super 6C that I mentioned in the earlier slides. Okay, now I'm going to be sharing with you a really interesting versus comparison between the running YOLO 5 on the Disk Pi Super 6C versus Turing Pi 2.0, and later on we'll be jumping into the conclusion and remark for the performance. So the first side, which is the left side, if you click here, you will see in front of you the Disk Pi Super 6C running YOLO. While the Turing Pi here, which is powered up in front of you, is doing the same job, we are running it. Let me tell you a story. What is this? So basically, I keep saying hardware, but I didn't tell you the software and the details of the software. It's a flight software community. So end of the day, you have to know, we are working hard on running Kubernetes as a scheduler in between all of the nodes shared inside these boards. And there's 2 Kubernetes versions, K3S and K8S. This is K3S because, that due to the limitation of memory and the power of computing. And, the dashboard in front of you for both sides, as you can see at the moment, is called RabbitMQ, which is basically the way that we are taking the frames from the cameras on both sides and pushing into the YOLO B-trained inference module it will be later on connected to the F prime, and then it will be connected to the NLP, so as a final end. And now we're going to be jumping into the performance. You will find here in the top the performance coming from the dashboard for the RabbitMQ for the Disk Pi, while the Turing Pi in the bottom. And let's go directly to the bottom of the point. The camera is a streaming of frames, right? So the incoming for the Disk Pi, it can be taken 14 frames per second, while in the Turing Pi is taken 1.4 per second. But I'm not using GPUs here. I'm just using Compute Module 4. There is a bunch of reasons we'll be jumping into it. Now, the module itself of the YOLO is running is 3.2 per second here, while there is running 0.20 per second for the processing of the frames information that we have. We expected some overheat coming from the Turing Pi because we didn't have heatsink and active cooling system, but in the Disk Pi that we have a cooling system, but it doesn't mean that Turing Pi is going down, but we didn't use GPUs in that case because, as I mentioned in the Jetson Nano, it was giving a headache a lot for the missing libraries and obsolete libraries and lack of support. To jump to the conclusion and sponsors, I would like to deeply thank NAFC, NAECC, Artemis for NASA, NASA Mind, Lockheed Martin, Cal Poly Pomona, and the lab that we are working for, which is a reconfigurable space computing lab at Cal Poly Pomona, for sponsoring this work and for the continuous support and encouragement for the student to work in the space and deep space applications. Thanks for everybody, and we are looking forward for any question. The floor open for the questions, and we are ready to answer. Thank you.